In the remote and economically challenged region of Papua New Guinea, an e-waste dilemma unfolds alongside significant poverty, limited healthcare access, and financial constraints. This multifaceted issue stems from discarded electronic devices like smartphones and laptops that take unpredictable paths due to the absence of proper e-waste management. The result is not just environmental threats, but also the endangerment of local communities' health and well-being due to the hazardous materials in e-waste. Moreover, informal recycling practices, while well-intentioned, inadvertently expose individuals to harmful substances. Handling and getting rid of dangerous waste in Papua New Guinea is still a problem. This is because toxic stuff and chemicals can harm people's health and the environment. In many places in Papua New Guinea, the water can get contaminated very easily with harmful substances because waste isn't managed properly.
Improper e-waste handling practices, including unsafe acidic neutralization using strong alkaline, have been conducted in various parts of the world, often resulting in negative environmental and health impacts. In some regions, due to lack of strict regulations and enforcement, e-waste recycling facilities have resorted to hazardous neutralization method. This not only endangers the well-being of workers involved, but also releases toxic substances into the environment, contaminating soil and water resources. It is essential to promote responsible and safe e-waste recycling practice globally, with a strong emphasis on compliance with environmental regulations to mitigate the adverse consequences of such activities. In this experiment, we dive into the growing issue as well as the introduction to the concept of e-waste. Our objective is to take an action immediately to manage e-waste, as failing to do so could lead to ongoing harm to both humans and the environment due to its toxic components. The objective of our investigation is to introduce a method that can be used to neutralize the harmful acidic components of e-waste in a safe and eco-friendly manner. We replaced strong acids and alkaline substances with vinegar and baking soda due to their less harmful properties. This shift allows for a safer and more environmentally friendly alternative, mitigating potential harm to both participants and the environment. Baking soda and vinegar were selected for their minimal environmental impact and ready availability, making the experiment accessible and easily comprehensible.
The aim of this experiment is to demonstrate how baking soda and vinegar can be used to neutralize the harmful effects of acidic e-waste components in a safe and eco-friendly manner. The materials needed for conducting this experiment are an old phone and keyboard to obtain 4 copper sheets and 4 circuit board samples, 25 grams of baking soda, 50 milliliters of vinegar, 2 small containers, gloves and goggles for safety, as well as pH and litmus paper. Begin by collecting e-waste from old devices like phones and wireless keyboards. Carefully open them to obtain the circuit boards and copper sheets while wearing safety goggles and gloves for protection. To ensure consistent results, standardize the sample masses using a precise balance scale, accounting for zero error. For example, set all copper sheets to a mass of 0.38 grams and group the circuit boards with 2 weighing 2.68 grams and the other 2 weighing 2.24 grams. Measure the initial pH of vinegar, typically around the pH level of 2. Accurately measure 50 milliliters of vinegar while maintaining the meniscus at its midpoint. Prepare 4 samples for each batch. Additionally, measure 25 grams of baking soda using a balance scale, ensuring zero error.
Pour the measured vinegar onto the e-waste sample and observe any fizzing or bubbling, indicating a chemical reaction. Then sprinkle 25 grams of baking soda onto the e-waste exposed to vinegar. As baking soda functions as a base, it can effectively neutralize acidic materials. Then observe how the baking soda interacts with the vinegar-treated e-waste. If there is reduction of the fizzing and bubbling, it indicates that the neutralization is successful. To assess the effect over time, split the samples into 2 groups, one for 24 hours and the other one for 48 hours, labeled well. After 24 and 48 hours, return to the samples and observe any changes, particularly regarding the fizzing or bubbling. Utilize pH paper or pH indicator strips to measure the pH of the 24-hour and 48-hour samples. Then we can conduct a litmus test using red litmus paper on each sample and observe any color changes. A shift to purple indicates successful neutralization.
After 24 hours, we could still observe a few bubbles on both the samples. The color of the red litmus paper did turn into purple, indicating neutralization happening, but the existence of bubble does indicate that the acidic components present in the e-waste samples were not fully neutralized, which proves the results shown in pH paper with a pH level of 6. After 48 hours, we could observe that there were no bubbles left to be spotted. The color of red litmus paper did turn purple, indicating neutralization happening, and the absence of the remaining bubbles fully proves that the acidic components present in both samples were fully neutralized. It was further proven with the results shown in pH paper with a pH level of 7 to 8. These results suggest that baking soda can effectively neutralize the acidic components in e-waste, making it a promising solution for safer and more environmentally friendly e-waste management. The longer exposure time led to a more complete neutralization of the samples.
The independent variable for this experiment is the time duration of exposure of e-waste in the baking soda and vinegar solution. The dependent variables from this experiment are the amount of fizzing after baking soda is added into the vinegar, and the pH levels that determined whether neutralization had occurred or not. The controlled variables in this experiment are the mass of e-waste samples used, the type and amount of baking soda used, and the type of and volume of vinegar used. While the uncontrolled variables from this experiment are the temperature of the environment where we kept our samples, the humidity of the sample surroundings, and inconsistent stirring or agitation. To evaluate our research, the further implementations that could be applied are this assessing the environmental impact and effectiveness of baking soda in the marine ecosystem, exploring the comparative effects, efficiency, and results of strong acids and alkaline substances rather than vinegar and baking soda with varying time durations, minimizing CO2 emissions, but not last and not least, analyzing the cost and economic impact of implementing the baking soda-based neutralization method on a large scale. And with that being said, we thank you so much for watching our presentation.